Bismillahirrahmanirrahim. Welcome to the Electrical Engineering channel. In today's lecture, I am going to discuss the spherical coordinate system of vectors. And in spherical coordinate systems, there are three components which are r, theta, and phi. And all these three components are perpendicular to each other. Here, r is the radial distance of the point from the origin. So in this figure, you can see these are the x, y, and z axis. If our point P is lying over here, then the radial distance from the origin will be the r vector, and the direction of r vector will be away from the point from the origin. So the unit vector which is pointing in the outward direction from the origin will be the direction of ar. Now the angle between this r vector and this z axis is called theta. So this angle is theta, so it is the angle between z-axis and r, and the direction of theta will be tangent to the point away from the z-axis. So this is a theta. So if our point is lying at z-axis, then theta will be equal to 0, and theta increases when this point moves along the sphere in the lower direction. So this angle theta will be increasing, and definitely the direction of theta is in the direction where theta increases. So it will be actually the direction in the tangent of this point away from the z-axis. Similarly, if our point lies over here, then the direction of a theta will be in this direction, tangent to the point. The third vector is actually phi, and phi is called the azimuth angle between r sine theta and x-axis. So here in this case, the r vector is directed from origin to the point P. In cylindrical coordinate system, we had the phi, and the phi was the angle uh, between rho vector and the x-axis. Here we have r sine theta component, the component of r which is in the direction of rho. So this r sine theta component is actually the component which is same as the rho vector in the cylindrical coordinate system. So how we have achieved these two components of r? So for example, this is r vector. This component will be r cos theta, and this component in front of the theta angle will be r sine theta, and this r sine theta is actually equal to rho vector in cylindrical coordinate system. So the direction of phi is same, and in the cylindrical coordinate system it was the angle between the rho vector and the x-axis, and in spherical coordinate system the phi is the angle between r sine theta and the x-axis. So the definition of phi is the same, and it is the azimuth angle. Similarly, theta is called a latitude measured from the z-axis and the r vector, and at point lying on the z-axis theta is equal to 0, and the direction of theta is tangent to the point away from the z-axis. Okay, so in cylindrical coordinate system, phi is the angle between rho and x-axis. Now we can calculate the conversion of the components between spherical and Cartesian coordinates. So from Cartesian coordinates, we can calculate the spherical coordinates using the expressions 1, 2, and 3. So r is equal to x square plus y square plus z square under root r cos theta is equal to z. And from this expression, we can calculate theta in terms of x, y, and z. So you can see from here that this z is equal to r cos theta. So theta is equal to cosine inverse z over r. So this is equal to cosine inverse z over x square plus y square plus z square under root. And phi is same as in the cylindrical coordinates, and it is equal to tangent inverse y over x. Similarly, x is equal to rho cos theta in cylindrical coordinates, and rho is equal to r sine theta in spherical coordinates. So x will be equal to r sine theta cos phi, and y is equal to rho sine phi, and it will be equal to r sine theta sine phi, and z is equal to r cos theta. So using these expressions 4, 5, and 6, we can transform spherical components to the Cartesian components. Now we will calculate the dot products of individual unit vectors among each other. So if we have a vector represented in spherical components, we can represent it as a is equal to ar plus a theta plus a phi. But if we are given the vector in Cartesian coordinates, it will be ax plus ay plus az. Now we have to individually calculate all these three components, a r, a theta, and a phi. and AR will be equal to whole A vector dot product with AR, this unit vector. Similarly, A theta will be equal to A dot A theta, and A phi will be equal to A phi A phi. And we know that A will be composed of all the three Cartesian components. So we have to calculate the dot product of AR vector with all three Cartesian unit vectors. So first unit vector will be AX. So AX dot AR must be calculated first, and AX dot AR will be calculated by using the following principle, that the magnitude of AX is actually equal to 1. So this is AX magnitude. Now we know that from this figure, this AR is actually directed in this direction, radially outward from the origin. Now this AR unit vector is actually not lying in the XY plane. So first we have to find out the component of AR which is actually lying in the XY plane, and that component will be AR sine theta. Just like the way we have transformed R into two components, this is R cos theta and this is R sine theta, and R sine theta is actually the component which is lying in the XY plane. So this is XY plane. Similarly, AR will have two components. This component will be AR sine theta and this component will be AR cos theta, and this component AR sine theta will be lying in the XY plane. So now we will calculate the dot product of AX with actually AR sine theta, because AR sine theta is the component which is lying in the XY plane. So we have to first bring this AR unit vector into the XY plane. Then we will take the dot product of that component with AX. So it will be AX multiplied by AR sine theta, and clearly the angle of AR sine theta with the x-axis is phi, right? So this is the top view. Here we have x-axis, here we have y-axis. This is the same top view which we also drawn for the cylindrical coordinate system. So this is phi and this is r sine theta, and the angle between this AR sine theta and AX will be equal to phi. So AX dot AR is equal to sine theta cos phi. Similarly, AY dot AR will be equal to sine theta cos 90 minus phi. So this angle is 90 minus phi, so it will be sine theta sine phi. And AZ dot AR will be equal to cos theta, because this is our AR, this is our AZ. The angle between them is theta. So AZ dot AR is equal to cos theta. So it is simple. Now we will calculate AX dot A theta, right? So again, this is AR and this is A theta, tangent to the point away from the z-axis. So again, we have to find out the component of A theta which is lying in the xy plane. So again, this A theta has two components, right? So this is A theta, and we know that this is the angle theta. So if this angle is theta, then this angle will also be equal to theta, right? So this is A theta, and the component in front of this angle theta will be A theta sine theta, and this component will be A theta cos theta. So this is A theta, and this component is A theta sine theta, and this component will be A theta cos theta. Now we know that this is z axis, this is y axis, okay, and this is A theta. So the angle between AZ and AR is equal to theta. Now this A theta is perpendicular to AR and this AY is perpendicular to AZ. So the angle between two lines is same as the angle between their perpendiculars. So the if the angle between AZ and AR is theta, then the angle between A theta and AY will also be equal to theta, because A theta is perpendicular to AR and AY is perpendicular to AZ. So this angle will also be equal to theta, and by looking at this angle, we can draw two components of this A theta vector, and this is A theta sine theta, this is A theta cos theta. So we will take the dot product of A theta cos theta instead of A theta. So this is AX dot A theta. So this is AX magnitude, and here we have A theta cos theta magnitude, right? And this is the angle between A theta cos theta and AX. So the angle between A theta cos theta and AX is equal to phi. So this is actually AR sine theta, and this is also the vector. If we have the top view, if we see this sphere from the top, then these AR sine theta and A theta cos theta will be in the same direction, right? Because we have drawn all the unit vectors over here. So this is actually a theta and this is actually AR. They are at the right angle if we have the side view. They are spaced at the right angle. But if we see these two vectors from the top, we will just see these two vectors in the same direction. So AR sine theta and A theta cos theta will be in the same direction if we have the top view. So as a result, we will have cos phi for AX dot A theta and we will have sine phi for AY dot A theta, as we had these values for the AX dot AR and AY dot AR products. So here we had cos phi and here we had sine phi. Again we have cos phi and sine phi, and this is sine theta and here we have cos theta. Now AZ dot A theta is equal to minus sine theta. Okay, so this is also very simple. This is AZ, this is A theta, so we can draw this unit vector over here. So this is AZ, this is A theta, and this is actually theta between AZ and AR, and the angle between AR and A theta is 90 degree. So this total angle between AZ and A theta will be 90 plus theta. So it is cos 90 plus theta, which is equal to minus sine theta. Now AX dot A phi is equal to minus sine phi, AY dot A phi is equal to cos phi, and AZ dot A phi is equal to 0. And these are the same values which we had for the cylindrical coordinate system. Now we will solve a few problems to get a deeper insight into the spherical components and their transformation to Cartesian components. So this is our first point C, and its Cartesian coordinates are minus 3, 2, 1. And this is another point D, and its components are given in spherical coordinates. And we have to find out spherical coordinates of C, so we will just calculate R, theta, and phi. And we know all the values of X, Y, and Z. So this is R, this is theta, and this is phi. So since this point is lying in the second quadrant, so phi will be equal to pi minus tangent inverse y over x. Similarly, we can calculate Cartesian components of this point, and x, y, and z can be calculated using the same expressions which we have just discussed. So x is equal to this, y is equal to this, and z is equal to this. Now in another example, we have to calculate the A vector field in spherical components and variables at this point. So we have to find out AR, A theta, and A phi. So AR will be equal to A dot AR, and it will be equal to 10 AX dot AR, and it will be equal to 10 sine theta cos phi. And theta and phi will be calculated from this point. Theta is equal to sine inverse Z over R, and phi is equal to 180 minus tangent inverse y over x. So by putting these values, we can calculate AR. Similarly, we can also calculate A theta, which is 10 AX dot A theta, and it is equal to 10 cos theta cos phi. Similarly, we can calculate A phi, and it is equal to minus 10 sin phi. And then we can add all these three components, and we can place unit vectors with each component. So this was the second very simple example. Now we will discuss the differential volume element in spherical coordinate system, and the differential volume element of spherical coordinate system will look like this. So in cylindrical coordinate system, we had a straight line, straight vectors along the z-axis, but in spherical components, we will have the curved surfaces along the z-axis. So this is the differential volume element in spherical components. Here this length will be along the r vector, and this will be called dr, and this will be actually r d theta, because the radius of this arc is actually r, and the angle, this angle is equal to theta. So this length of the arc will be equal to s is equal to r theta. So this is the radius of this curve, or radius of curvature is r, and the angle is d theta. So the differential length of this vector is r d theta. Now this is the third component or third length, and the radius of curvature of this arc is equal to r sine theta, and the angle from this point up to this point, the differential angle is d phi. So the total arc length in this direction is r sine theta d phi. So if we know these three lengths, differential lengths along all the three components, we can calculate the differential area of each differential surface, and we can also calculate the differential volume of this entire element. So first of all, let's calculate the differential area of each of the six surfaces. So the for the right surface, this is the right surface, One element is dr, the other element is rd theta. So the differential area for the right surface is rdr d theta, and phi will be constant for this phase, and phi will be equal to phi 1. Similarly, for this phase, phi will be equal to phi 2, and the differential area will be same. For the bottom surface, theta will be equal to theta 2, and it will be constant, and the differential area will be equal to, this is dr, and this is r sine theta d phi. So r sine theta dr d phi, and theta is equal to theta 2. And for the top surface, theta will be equal to theta 1, and we will just have to multiply r sine theta d phi with dr, and we will get the same differential area. Now finally, for the inner and the outer surfaces, the differential area is equal to r d theta and r sine theta d phi. So if we multiply these two components, we will get r square sine theta d phi, and r will be equal to r1 for the inner surface, and for the this outer surface, the differential area will be equal to r square sine theta d phi, but r will be equal to r2, and r2 is the constant for the outer surface, and r1 will be the radius, and it will be constant for the inner surface. Similarly, the differential volume can be calculated by multiplying all these three differential lengths. So dr, r d theta, and r sine theta d phi. So the product will be r square sine theta dr d theta d phi. That will be the differential volume. Now in this problem, we can calculate the total volume of the differential element. We can calculate the surface area of all the six surfaces, and we can calculate the differential lengths. Um, so in this problem, uh, a differential volume element is given in which r is varying from 2 to 4, theta is varying from 30 degrees to 50 degrees, and phi is varying from 20 degrees to 60 degrees. And the differential volume can be calculated by using this expression r square sine theta dr d theta d phi, and by evaluating the triple integral of this expression, we can calculate the total volume, and it is equal to 2.91. Similarly, the total area can also be calculated for the right surface, and it will be equal to this value, and for the left surface, it will be the same. For the top surface, it will be equal to this expression, and theta will be equal to 30 degrees, and for the bottom surface, theta will be equal to 50 degrees, and the rest of the expression will be same, and the final answer will be equal to 3.2 for the bottom surface. And similarly, for the inner surface, r square sine theta d phi has to be integrated, and r will be assumed at 2, and theta and phi limits will be substituted in this double integral, which is called a surface integral. And for the outer surface, r will be assumed as 4. So all the answers are given over here. We can add all these areas to get the final total area. Now the total length of the 12 edges can be calculated by using this expression. So along the r vector, there are four edges, right? This is first edge, this is second edge, this is third edge, and this is the fourth edge. So these are the four edges along the r vector, and we are given four edges along the theta axis. So this is one vector along the theta axis, this is second vector along the theta axis, this is the third vector along the theta axis, and this is the fourth vector along the theta axis. And similarly, we will have four vectors along the phi axis, and this is the one first vector, this is the second, this is the third, and this is the fourth. So there are four lengths along all the three components, or all the three vectors. So along dr, all the lengths of the edges will be same. So we have to integrate just dr from 2 to 4 and multiply it with 4. Similarly, there will be two edges in which r will be equal to 2, and there will be two edges in which r will be equal to 4 along the theta axis. So just put these limits, and we will get the answer. And along the phi axis, we have two constant values, right? R and theta. So r will be equal to 2 and theta is equal to 30 degrees. This is the first edge. R equal to 4 and theta equal to 30 degrees. This is the second edge. R equal to 2 and theta equal to 50 degrees. This is the third edge. And r equal to 4, theta equal to 50 degrees. This is the fourth edge. And we have to just put the limits of phi, which are 20 to 60, and all these four components will have to be calculated individually and then added together, and finally we will get this answer. Okay, so I think that should not be too difficult. So this is r d theta. This is also r d theta. For the inner two edges, the value of r will be equal to 2. For the outer two edges, the value of r will be equal to 4. And we can calculate these lengths and multiply them by 2 for r equal to 2, and then we can calculate the length of the edge for r equal to 4 and then multiply them also with 2. Similarly, for this length along the phi axis, we have r sine theta. Now, for this edge, r is equal to 2 because this is the inner edge, and theta will be equal to 30 degrees. Similarly, for this edge, theta is equal to 30 degrees and r is equal to 4. And now for this, r is equal to 2 and theta is equal to 50 degrees. And for this edge, r is equal to 4 and theta is equal to 50 degrees. So all these four edges along the phi axis have to be calculated individually. So that's what I have done over here, and the total length is equal to 17.49. In the final part, we have to calculate the length of the longest straight line, and that is also not too difficult. So if we consider the shape of a cube, then we can calculate the length of the longest straight line by joining the line from one corner to the opposite corner in the opposite or at the opposite face. So for example, if we join this point with this point, then that will be a diagonal passing through the center of the cube, and that diagonal will have the longest length. Similarly, if I join this point to this point, so this is the top corner of the front surface, and this is the bottom corner of the back surface. So if we join these 2 points by a straight line, that line is also passing through the center, and that line will also have the longest length. So we have to do such thing for this differential volume element of a sphere, and for the sphere, I have considered this point P and this point Q. So if I draw a straight line from this P and Q, that line will have the longest length. Okay, so these are the coordinates of point P. R is equal to 4 because this is the outer edge. Theta is equal to 30 degrees and phi is equal to 60 degrees because theta varies from this direction. So for this surface, theta is equal to 30 degrees. For this surface, theta is equal to 50 degrees, and phi actually varies in this direction. So for this face, phi is equal to 20 degrees, and for this face, phi is equal to 60 degrees. So looking at this information, we can say that this point has the coordinates of 4, 30, and 60, and this point has the coordinates of 2, 50, and 20. So these 2 points must be first converted to the Cartesian coordinate system. So these are the Cartesian variables, and then we will have to multiply the distance formula and calculate the distance between these two vectors, and that distance will be calculated as 2.53. So in this way, we can solve such a problem on the spherical coordinates. And in spherical coordinate system, we have these three differential lengths, and the limits of these three components are r actually varies from 0 to r, and theta varies from 0 to pi, and phi varies from 0 to 2 pi. So we can also calculate the area and volume of a cylinder and area and volume of a sphere. These are the actually expressions which we already know, but how we can calculate and or how the analytical expressions for these quantities have been obtained, we can also check by using these cylindrical and spherical coordinate systems. So in the cylinder, if we want to calculate the area of a cylinder, surface area of a cylinder, then we have to do this integration, and rho d phi dz. If I integrate this expression, rho is constant and phi actually varies from 0 to 2 pi, and z varies from 0 to L. L is the length of the cylinder, and it will be equal to rho into 2 pi L, and it is equal to 2 pi rho L. And rho is the radius of the cylinder, so it is a famous expression for the area of the cylinder, and it is equal to 2 pi RL. or 2 pi rho. Similarly, volume of the cylinder can be calculated by using this expression rho d rho d phi dz. If I take the triple integral of this dv, I get this pi r square L. So pi r square L is the famous expression for the volume of the cylinder. Similarly, area of a sphere can be calculated by using this expression. So r square sine theta d phi. If I integrate this expression from psi theta from 0 to pi and phi varying from 0 to 2 pi, and it will be equal to 4 pi r square. This is the famous expression for the area of the sphere, and the volume of the sphere can be calculated by evaluating this triple integration r square sine theta dr d theta d phi, and by performing this integration we will get volume of the sphere equal to 4 by 3 pi r cube. This is also the famous expression for the volume of the cylinder sphere, and this is how the areas and volumes of cylinder and sphere are actually calculated. And it is a very simple calculation if you know all the mathematics behind developing these two coordinate systems. So I hope that lecture was very informative for you. For watching more lectures, please subscribe to this channel. Until the next lecture, it's goodbye.